apple pies, and household radiators. What do you do when you're the proud owner of an ultra-luxurious vintage automobile that has an original steering wheel that's several miles short of being as elegant as the car? You order yourself a handsome custom-made steering wheel designed to match the vehicle's deluxe interior. From the plain original steering wheel to a deluxe edition befitting a vintage automobile, custom matched to its woodwork and leather interior. They start by skinning the original wheel, a steel ring covered in black plastic with some leather trim. After slicing and chiseling off the covering, they file the ring clean because they'll be reusing it for the new wheel. However, they'll encase it within 2 plywood rings to beef up the width and thickness, and to create a substrate on which to glue the wood veneer. Using a jigsaw and bandsaw, they cut a front ring and a back ring out of European birch plywood. Then they mill the profile, including a groove inside for the metal ring. Once the shape is finalized, they sand the surface smooth to prep it to receive the wood veneer. Veneer is made from a piece of wood sliced into ultra-thin sheets called leaves. For each steering wheel, they take 4 consecutively cut leaves so that their wood grain pattern is nearly identical. For each plywood ring, they take 2 of those leaves and tape them mirror image to each other. They insert adhesive where the taped edges meet and let it dry overnight. Then they lay the ring pattern onto the veneer, trace and cut out the shape. Next, they notch the veneer ring so that it can fold over the ring's edges. After coating the plywood ring with glue, they center the veneer and tape down the edges. Next, they add a layer of protective plastic, followed by rubber cushioning. These will protect the veneer surface in the next machine. A vacuum press. Powerful suction draws the bag tightly around the materials. This locks the veneer onto the plywood substrate, forcing out any air in between them which would hinder full adhesion. Each plywood ring is now veneered and ready to encase the metal ring of the original steering wheel. The workers apply glue to the underside of both rings, into the groove. Then they assemble the 2 veneered rings over the metal one. They set clamps all around and leave the glue to dry overnight. The next day, they remove the clamps and put the steering wheel in an oven for about 8 hours to cure the glue. Once the steering wheel cools, they file away excess glue that seeped out the seam, then sand the entire surface silky smooth. They protect the delicate veneer with 8 coats of resin, cured in the oven for optimal durability. Then they polish the surface with a series of compounds to produce a glossy finish, which highlights the richness of the wood grain. The perimeter of the steering wheel now completed, they cover the spokes and hub with fine leather. First gluing the pieces, then hand stitching them. They put back the original steering wheel's hub, which they had removed before the makeover. Then the finishing touch, a veneered horn button. After all, when you're driving a luxury car, you might just want to toot your own horn. Be they airplanes, satellites, or rockets, aerospace vehicles all have one thing in common, besides their capacity to fly. Their internal construction includes several assemblies of tubes and ducts through which materials such as fuel, air, oil, and hydraulic fluid move. Aerospace tube and duct assemblies are typically made of highly durable, lightweight materials, such as aluminum and titanium. The choice of material depends on the application. For example, whether the finished component must be able to resist high heat or withstand high pressure. These aluminum tubes are on their way to becoming a fuel line for a Boeing 737. The operator immobilizes a tube with clamps, then saws it to the length required. This leaves burrs, sharp shards on the cut edge. So they insert the tube into a deburring machine. Here's what the tube looks like before deburring and after. They squirt some lubricant inside, then slide the tube onto the mandrel of a computer-guided bender. As the machine forms the tube to the required shape, the mandrel provides counterpressure, preventing the tube walls from collapsing inward. They'll repeat this process with all the tubes which make up the fuel line assembly. They clamp each part into a fixture, then pass a laser measuring device over it. With utmost precision, the laser analyzes the dimensions from 5 different angles to ensure the part meets technical specifications. Next, workers submerge the part in hot water and cleaning solution, then rinse twice. This washes away the lubricant and any dirt. Now the high-tech precision work can begin. A robotic laser cutting system finalizes the shape and cuts all the required holes and slots. Just a bit of pressure, and the cut pieces easily pop out. Meanwhile, a stereolithography machine makes the fixtures, which will position the various parts of the fuel line together for welding. A computer-guided laser beam repeatedly flashes the shape of the fixtures onto liquid ceramic. Each flash solidifies a 250th of an inch thick layer of the liquid. Thousands of hardened layers later, the weld fixtures are fully formed. Welders use these ceramic fixtures to correctly assemble the connecting fuel line components. Once everything's precisely in position, the welding begins. For aircraft safety, it's critical that every fuel line be leak-free. To test for leaks, they fill it with nitrogen at high pressure, submerge it in a water tank, then watch closely for bubbles, which would indicate nitrogen escaping. They use nitrogen rather than air because its molecules are smaller, making it possible to detect smaller leaks. After this, they heat treat the fuel line to harden the metal and apply an anti-corrosion coating. They wrap the fuel line with high heat-resistant foam insulation, secured with high heat-resistant polyester tape. This insulation prevents fuel from freezing in cold temperatures. It also blocks heat coming from other components of the aircraft, keeping the fuel at a safe working temperature. After a final inspection, the fuel line is ready to be shipped to the customer. It leaves the factory with a few uninsulated spaces for installation clamps. These areas will get insulated after the fuel line is mounted in the aircraft. The apple pie is a mouth-watering treat. This pie's popularity has been centuries in the making. It dates back to the 14th century, when countries like England, Denmark, and Sweden developed slightly different versions, all leaving fans hungry for more. Today, apple pie is mass-produced to meet demand, so you can throw away your rolling pin and let the folks at the factory do all the work. To make the filling, they empty loads of apple slices into a huge steam-heated kettle. These apples are a firm and tart type and have been organically grown. They add honey and apple juice, and the apple slices simmer in the liquids, while mixing blades gently blend the ingredients. And with the slices now partially cooked, they spice up the mix with a generous dash of cinnamon. To thicken it to a syrupy sweetness, they add tapioca flour. The blades fold the dry ingredients into the mix as the apple slices continue to cook. The fruit softens and releases juices. The liquids thicken to a syrupy consistency. When the apple slices are lightly browned, this filling mix is done. These browned and syrupy slices are now prepared and ready for the pastry shell. The shell starts with chilled premium-grade butter. It's the creamiest. Organic and 100% whole wheat flour is the next ingredient in this high-fiber pastry recipe. They pour a measured amount of honey into the pastry mix to sweeten it. They add ice-cold water. It's cold to keep the butter from melting too quickly, and that means the crust will turn out flaky. Inside the pastry mixer, a dough hook blends and kneads the ingredients until they congeal into dough. The dough is moist, but not too wet and sticky. Inside an apparatus called a sheeter, a mechanized roller presses the dough into sheets. A worker drapes a sheet of dough over groupings of 4 paper pie plates, which then move forward on a carousel. Meanwhile, overhead, that syrupy apple filling funnels into a device called a depositor. The depositor pumps the filling into the uncooked pie crusts as they circle around on the looped conveyor. This automated system fills every second grouping of crusts right on cue. Now full of sweet fruit, a worker tops them with more dough, giving the pies the upper crust. Like a big revolving cookie cutter, a rolling die punch cuts the dough around the pie plates, separating them, trimming and crimping the edges, all in one action. Pedestal lifts hoist the pies, and a worker transfers them to the next conveyor. They finish one group of pies and then start another, for a continuous cycle of pie production. The pies now head into the baking zone. Here, workers arrange the pies on baking sheets. They slice holes in the top crust to vent steam and prevent fruit juices from overflowing. They stack the pie-laden baking sheets on racks in a convection oven. The racks spin for a more even baking job. They send 1 apple pie from each batch to the quality assurance department. Here, the inspector takes in the aromas from the freshly baked pie. She examines its form and compares it to an existing perfect pie. Slicing it confirms that the crust is flaky. But does it have that melt-in-your-mouth flavor? There's only one way to verify that. If the quality assurance people approve the pie, then the whole batch moves forward. They flash freeze the pies, then seal them in cellophane. Suctioning arms open cardboard containers, and a worker slides in the pies. Rollers close the pre-glued flaps. They produce more than 2,100 apple pies every hour at this factory. Once the job is done, there are big decisions to be made, like one scoop or two, one slice or the whole pie. Perhaps it's best just to dig in and decide later. Invented in 19th century America, the radiator brought warmth to people's lives. It made central heating possible. Before that, several fireplaces and stoves were needed to warm a home. But with a radiator in every room, one boiler could heat an entire house. While the traditional cast iron radiator is still a source of warmth, it now competes with modern steel versions. These steel radiators are lighter and heat a room faster. They also come in a range of styles and can make a colorful design statement. Production begins with a series of powerful punch presses. They punch holes in steel plates, and they shape the parts by pressing the metal onto dies. These punched and pressed parts are called half pieces. They'll be used to make radiator headers, the connector part that interlinks the tubular heating elements. The half pieces exit the punch press station and slide into the clutch of a robotic device. It brings two half pieces together in perfect alignment and delivers them to an automated welder, which joins them at the seam. The process is usually shielded by a protective cover, but it's been lifted to allow our camera to video it. Next, a press pairs down the bulging seam. This is called deburring. With perfect timing, a robot then moves in and transfers the assembly to a grinding station. Here, it rotates between two sanding belts to smooth the seam to a flawless finish. A circular saw spins towards the part and slices it in the center to create two radiator headers. These radiator headers are now complete. A gripper with rounded claws transfers 6 steel tubes to a welder. The welder fuses the tubes to the headers, and while the welding is being done, another feeder robot ensures a steady supply of headers. There's one header for 2 tubes, so 3 radiator modules are coming together simultaneously. Sharp, pincer-like knives shear down the protruding welds, so they're flush to the rest of the parts. The welded modules then chafe against 2 grinding belts. The process smooths the seams substantially. But this grinding misses the spaces between the steel tubes. So a smaller sander tucks into that location, making the weld smooth all the way around. Now a test. They immerse a 4-element module in water and pump air into it. No bubbles in the water mean no leaks, and production continues. They now build the radiator section by section. They layer the modules and weld them together at the headers. This sectional approach allows them to assemble radiators of virtually any size. Each radiator is custom ordered to fit into a specific space and to meet a specific heating need. Of course, the larger the radiator, the more heat it delivers. Here's an inside look at a steel radiator header. With the radiator now complete, they repeat the test done earlier and confirm that it's completely leak-proof. They now run an electrical charge through the radiator as they immerse it in a primer. The charge causes the primer to cling to the metal. Once baked on, it will protect it from corrosion. This household radiator is ready for a coat of paint. The customer selects the color beforehand to suit the home's interior design and his personal taste. They bake on the finish, and once it cools, they wrap up the job. These radiators are now homeward bound. Fueled by a furnace, hot water will move through them in a continuous loop, and they'll exude warmth. That's why the radiator continues to be a nice thing to come home to. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at sciencechannel.com/howitsmade.